Hello, everyone. Today I'd like to talk about the shear strengthening uh, of the critical RC beams using mortar-based composites. I'm Xiangsheng and my supervisor is Georgia and Chao, and we are from University of Nottingham. The outline of my presentation is the following. I will start by explaining the background and motivation, continue with the aim and objectives for the study. Then I will present the experimental program with the main test results, and the last part will be the conclusions. Firstly is background and motivation. Most of the exciting building and bridge stock in Europe and worldwide was designed according to old standards using poor materials and construction practice. These structures present inherent deficiencies, which increase their vulnerability, like insufficient shear reinforcement, which may lead to shear failure, a brittle mode of failure which occurs suddenly and without any signs, and may cause great harm to life and property safety. Therefore, we aim to extend the service life of these structures by making them more resilient to natural hazards like earthquakes. But how do we manage that? By retrofitting and stressing them. With the development of new composite materials, FRP jacketing has become a very popular intervention system in strengthening deficient structures. However, this system has many shortcomings, mainly related to the use of resin. Its failure resistance and high temperature resistance are poor. Moreover, it cannot be applied to wet surface. Therefore, in order to resolve these issues, experimental studies were carried out to explore the effectiveness of composite systems where mortar is used instead of resin. Thus, FRCM system was developed, where composite textiles are embedded in mortar. And recently, studies have used ultra-high performance fiber-reinforced concrete and ECC in the form of externally bonded reinforcement in strengthening applications. And for FRCM system, it can be divided into three categories: TRM, PBU, FRCM, and SRG. The main difference between them is the type of textile. And as shown in the picture, the commonly used textiles are carbon, glass, basalt, PBO, and steel. Regarding the jacketing configurations, we may use the foliar wrapped and UV wrapped and set bonding. Then is aim and objectives. Recent studies have demonstrated the effectiveness of mortar-based composites. However, the research on the effectiveness of SRG and the UHP FRC jacketing system on improving the shear performance of RC beams is limited. So the experimental program carried out aims to investigate the shear performance of SRG, UHP, FRC strength RC beams through a series of 3-point bending tests under monotonic loading. And the SRG system is compared with the SRP, where the steel textile is embedded in resin. And the most studied mortar-based composite system, the carbon FRCM. Then I want to talk about experimental program. This part is the introducing of strengthening systems. Parameters of study were the compressive strength of concrete equal to 25 and 60 megapascal at 28 days. Different textiles, such as steel and carbon, were used. The density of ultra-high tensile strength steel textiles was 4 and 8 cos per inch. And the number of the carbon textiles are 2 and 3 layers. And we also use U-shaped and fully wrapped as the strengthening configurations of the jackets. The density of UHTSS, which is a very important parameters for SRG, because it affects the bond quality between the textile and the matrix. If the density is too high, the mortar cannot flow freely, so it may result in poor adhesion to the textile and reduce the shear enhancement capacity. In addition, I would like to note the following. Firstly, SRG, SRP, CFRCM are external bonded jackets, and the UHP FRC is near surface and bonded system. And for the B2 beams system, which compares different textiles, can be compared based on their axial stiffness. In our study, the ratio of the axial stiffness of the CFRCM over the steel textiles received two values, 0.75 and 1.30 for the 2-layered and 3-layered CFRCM jacket, respectively. In this project, we use 4 systems: is SRG, CFRCM, UHP, FRC, and SRP. And the property of materials as shown in the table and provided by manufacturer. In this slide, you can see the various steps of the application of the SRG, SRP, and CFRCM. And this is for the UHP FRC jacketed beams. During the construction of the beams, an indent equal to the thickness of the concrete cover equal to 10 millimeters was created, so that the UHP FRC jacket could be applied as a near surface embedded system. Then is the test setup part. 50 beams were constructed in total. All have the same geometry with a shear span radius equal to 2. And the shear span length is equal to 350 millimeters. And this area do not have any strap-ups to promote shear failure. Moreover, it was not in the objectives of this study to investigate the interaction between internal strap-ups and the mortar-based composite systems. For SRG, SRP, and the CFRCM, there are 2 strengthening configurations, U-wrapped and fully wrapped. And for UHP FRC, it's just U-wrapped. For the name of the spacemans, the N corresponds to the control beam, M stands for mortar matrix, whereas P for resin matrix. H responds to high density steel textiles, L is low density. C stands for carbon textile, U corresponds to U-shaped jacket, and W to fully wrapped. The number at the end corresponds to the number of the layers of the textiles. And this is the test setup. This area, this red colored area is the strengthening and the deficient area. And we use LVDTs and the DRC. Then its results. This table summarizes the experimental results and the failure modes. The simple S stands for the shear failure. SD corresponds to shear detachment failure, and FR is flexural rupture failure. Regarding the strength increase, the maximum value appears in 1-layered fully wrapped SRP system strength B2. It is 176%, and the minimum is just 37%. in two-layered U-shaped SRG B1 beam. For B1 beam, as expected, the control beam field in shear varies both being retrofitted with SRP and SRG field in shear due to the detachment of the textiles. And the load deflection curves are present in this graph. The black colored curve corresponds to the control beam. The red colored curve corresponds to SRG and the blue is SRP. Impact of SRG and SRP strengthening was similar, with the SRG system leading to strength increase equal to 47% and the SRP to 49% and the SRP for 47%. Now we can say the B2 beams. Firstly is the SRG system. The load deflection curves of the beams strengthened with SRG system are present in this graph. And also the black one is the control beam. And it records that the axial stiffness of the two-layered low-density steel jackets is the same as the single-layered high-density jacket. Hence, the two systems can be directly compared. For the two curves, this one, the low, is the U-shaped jacket. The peak strength of the two-layered low-density jacket is a bit higher than that of the single-layered high-density jacket. And for the other one, the other two curves corresponds to folio wrap SRG jackets. And we can say due to the high density of steel textiles, the small gap between the cores imposes difficulties in the penetration of the mortar through the textiles. As a consequence, there were difficulties in the application with both the U-shaped and folio wrap jacket. And this is more evident in the response of the folio wrap jacket, where the beams feel due to textile detachment, whereas the lower density folio wrap jacket modifies the response of the beam from brittle to ductile. Then is SRP system. In this case, the U-shaped jacket shear detachment was observed. And in case of folio wrap jacket, the mode of failure changed from brittle to ductile. In this graph, the SRG system is compared to the SRP system for the case of the high-density steel textiles. In case of the U-shaped jackets, the peak strength is almost the same. In case of the folio wrap jackets, the SRP performance is much better than SRG. As discussed in the previous, the high-density textile imposes difficulties in the application of the jackets. Hence, it seems that for a high-density UHTSS textiles, a reason matrix works better than the mortar. And then is the CFRCM. This four line presents the force deflection response of U-shaped and folio wrap beams with two-layered and three-layered CFRCM jackets respectively. All beams filled in the same way by shear detachment. The typical mode of failure is shown in these photos. And you can see the ink-light cracks on the surface of the jacket. And removing the cracked mortar, the carbon fiber will not rupture. There's also the preparation between CFRCM and SRG. Now we can say all strength beams filled in the shear due to textile detachment except the folio wrapped two-layered low-density SRG jacketed beam. The folio wrapped beams with 2 and 3 layers of carbon textile reached the higher peak strength, whereas for the U-shaped, the response of CFRCM was similar with the SRG jackets. And in case of the UHP FRC, the 10mm jacket managed to increase the peak load by 122%, and the mode of failure was also detachment. Finally, is conclusions. From this, we can say all strengthening systems are effective. The peak load is increased from 37 to 176%. And in this case of SRG system, the density of the steel textiles should be less than 8 cos per inch, since the distance between the cos is a key parameter for the successful application of the system. The mortar matrix is used. And for SRG SRP system, fully wrapped jackets can modify substantially the response from brittle to ductile. The higher the compressive strength of the beam, the less effective the strengthening system are. Finally, I would like to thank very much Mapei and Carico for providing the materials. Thank you.